These are my recordings for chapter 16, and this is problem A, which says, have you ever listened to an approaching train by kneeling next to a railroad track and putting your ear to the rail? So here's this person who is putting his ear on the rail, trying to listen if the train approaches. I don't think that's advisable, but I guess that's what the problem is. Young's modulus for steel is y equals 2 times 10 to the 11 Newton per square meter, so I'm going to write that down. Let's see, y equals 2.0 times 10 to the 11 Newton per square meters. There we go. And the density of steel is rho equals 7,860 kilograms per cubic meter. On a day when the temperature is 20 degrees Celsius, how many times greater is the speed of sound in the rail than in the air? There's a number of equations in this chapter, but only one of them makes sense, which is the one for a solid that says has a Young's modulus and the shape of a long slender bar, and of course we can look at this railroad track and say, hey, that looks like a long slender bar. So we can use this equation, and from there it's of course straightforward. It's the velocity, the speed of sound, equals the square root of y over the density, and take the square root, equals, and then you plug in the answers and you're going to come up with something, and the units should be meters per second because everything is in standard units, so meters per seconds. By the way, you're going to come up here with a certain result, but that tells you that the sound in the solid is going to go at this kind of speed, which is compared to a gas quite a bit higher. But it doesn't tell you how far the train is going. I'm sorry, how fast the train is going and how far away it is. Maybe you could figure out the speed of the train with the Doppler effect, and maybe for the distance you would need a visual anyway. Okay, next problem. Chapter 16, problem B. This is about helium. And it says, at what temperature is the speed of sound in helium, which is an ideal gas with gamma equals 1.67? So gamma equals 1.67. Atomic mass, so m equals 4.003. U, which stands for atomic mass unit, sometimes it's also abbreviated as AMU. So at what temperature is the speed of sound in helium the same as its speed in oxygen at 0 degrees Celsius? So same V as the V, so for helium, as the V for O2 at 0 degrees Celsius. So this one here therefore says V helium at some temperature T equals V O2 at 0 degrees Celsius. So, and it asks for what that temperature is. Well, when we look at all the variables involved, and noticing that this is a gas, it pretty much narrows it down to just one equation that we can use, which is the one for the speed of sound in air. Respectively, for an ideal gas, it's set that too. So V equals gamma kT divided by m, take the square root, and because we have to figure out what t is. Whoops. Okay, I didn't mean to highlight it like that, but I guess that's what I did. It's alright. Huh, okay. Anyway, so solve this one here for t. You can do that in one step or in more steps. Should come out to, let's see, mass times velocity squared divided by gamma, the adiabatic coefficient, and divided by k, which is the Boltzmann constant. And now pretty much what you need to do here is, I'm going to pull this over here because I need a little bit more space, is that the gamma is given here. The k you have to look up in the book. So the Boltzmann constant, top of my head, what is it, 1.38 times 10 to the negative 23 joules per Kelvin. So what I just said, 10 to the negative 23 joules per Kelvin. Okay. Then the mass you have to convert to kilograms. So you have to see how much is an atomic mass unit. So you have to multiply this one here by the conversion factor, which is 1.66 times 10 to the negative 27 kilograms per atomic mass unit. And then you're going to come up with something here, a really small number here, right? I think I can give that much away, 10 to the negative 27 kilograms you should come up with. Of course, it's a very small number because this is just for one helium atom at a time. And by the way, helium is a monatomic gas, so the mass that we plug in here for one particle is just the mass for one helium atom. And then the only other thing here is the velocity. Well, that's the velocity of O2 at 0 degrees Celsius. So this one here, I'll look up in a table. And that is in the chapter where it says that the velocity, the speed of sound in oxygen 0 degrees Celsius is 316 meters per second. And then it's just a matter of plugging in these numbers and you come up with some kind of temperature for helium. Aside from this particular problem, which asks for the temperature, of course what comes to mind is what happens when you inhale helium, and I'll show you a little text here in a moment that actually advises that you shouldn't do this on your own, but that you should know what you're doing because it can be very dangerous. I'll read that to you in a moment. In any case, look at this one here at the equation that we use, V equals gamma kt divided by mass, take the square root of that, and notice that the mass of helium, the atomic mass, is much smaller than that of oxygen. So for helium it's roughly 4. For oxygen it's 32. For nitrogen it's 28 with an average of about 29. So in normal air, that mass of helium is about just 1/7 than that of normal air. And because it's in the denominator, it makes this fraction here 7 times larger. Take the square root of 7, that's roughly 2.6. So that means that at regular temperatures around T equals room temperature 20 degrees Celsius, you would take 2.6, so V helium equals 2.6 times the regular number that you find at 20 degrees Celsius, 343 meters per second. By the way, this is a 2.6 here. And when you multiply that, you see that you come up with something like 800, right? Maybe 900. Yeah, close to 900. So 890 meters per second. Okay, and now you apply the equation that links frequency, velocity, or speed of sound, and the wavelength. So V equals V times lambda, and notice that if this one here is quite a bit larger, then this one here is larger by the same amount, with the lambda here being the wavelength of the standing wave that you get in your vocal tract. So here's a little text that says the speed of sound in helium is nearly 3 times the speed of sound in air because the fundamental frequency of a gas-filled cavity is proportional to the speed of sound in gas. When helium is inhaled, there is a corresponding increase in the pitches of the resonant frequency of the vocal tract. That's pretty much what I said a moment ago, and it showed you a calculation. This causes a reedy, duck-like vocal quality, the opposing effect, and so on. And then it says inhaling helium can be dangerous if done to excess, since helium is a simple, I don't know how to pronounce this, asphyxiant, and so displaces oxygen needed for normal respiration, and so on. It can cause death, and there have been some fatalities in the past, so I advise not to do that on your own, as you probably don't have the expertise to do that. And by the way, I've never tried it myself. Okay, here we go. I'm going to see if this records actually.
Helium is a colorless, odorless, tasteless, non-toxic, inert, monatomic chemical element that heads the noble gas series in the periodic table, and whose atomic number is 2. Its boiling and melting points are the lowest among the elements, and it exists only as a gas except in extreme conditions.
I actually don't know if that recorded. All right. And of course, what I showed here is just on top of the original problem.